The next section is on atoms, molecules, and ions. We're going to talk about atomic theory and some of the ideas that scientists had many years ago about atoms, and as well as how that theory has evolved over time. We're also going to discuss the structure of atoms, chemical formulas, a bit more about the periodic table, molecular and ionic compounds, and chemical nomenclature. The concept of atoms was first proposed by the Greek philosophers in the 5th century BC. Atomos was derived from the Greek word indivisible. Later, Aristotle and others believed that matter was from these four different elements: fire, air, earth, and water. Uh, Much later, though, John Dalton proposed the atomic theory. And it can be summarized in these five postulates. Uh, Matter is composed of small particles called atoms. An atom is the smallest unit of an element. Elements consist of only one type of atom, and it's the same for all the atoms in that element. So here we have a copper penny. This is made just of copper, and these are the copper atoms. Atoms of one element are different in properties from atoms of other elements, and these are sort of self-explanatory if you know about atoms. But this is what John Dalton proposed for the first time. A compound consists of atoms of two or more elements combined in a small whole number ratio. So this means that we can write compounds like H2O as a ratio. So there are two hydrogens for every one oxygen atom. In a compound, the number of atoms are always present in that same ratio. And the fifth postulate is that atoms are not created or destroyed during a chemical change. They only rearrange to yield different types of matter. And this is copper 2 oxide. This is a black powdery compound, and it's two different types of atoms. It's copper and oxygen. And we can see the copper is in brown and the oxygen is in red. And this is a 1-to-1 ratio. That means for every one copper atom, there's one oxygen atom. If atoms aren't created or destroyed during a chemical change, the total mass of matter present when the matter changes from another type, one type to another, is going to remain constant. And this is called the law of conservation of matter. And I believe we went over this previously, but it means that nothing can be created or destroyed in chemical reactions. The law of definite proportions, or the law of constant composition, says that all samples of a pure compound, they have the same elements in the same proportion by mass. So here's an example here of isooctane. So here we have sample A, there's carbon and hydrogen. If we reduce this, so if we write this as the ratio given to us, it would be 14.82 divided by 2.78. So that would be carbon to hydrogen. This is for sample A. Would be 14.82 divided by 2.78. And if we reduce that, get 14.82 divided by 2.78, and that's equal to 5.33. And that's still carbon to hydrogen. Now, when we get a number like that, that means 5.33 over 1. So we've essentially found the unit rate of carbon and hydrogen here. And this is isooctane. So this is going to be consistent with what isooctane is. So if we check B and C, we will also get 5.33 grams of carbon for every 1 gram of hydrogen. The law of multiple proportions says that when two elements react to form more than one compound, a fixed mass of one element is going to react with masses of the other element in a ratio of small whole numbers. So for example, compounds that have chlorine and copper. A green solid has 0.558 grams of chlorine and 1 gram of copper. A brown solid has 1.116 grams of chlorine and 1 gram of copper. So we can write sort of a double ratio, if you want to call it that. This is actually called a complex fraction, but we can write so we have the ratio for the green of chlorine to copper, and we write that on the top. And I've already crossed these out, so we write the first ratio there. But what happens is the 1 gram of copper and the 1 gram of copper ends up canceling out. And the way that it does that is we multiplied the top by 1 gram of copper, and we multiplied the denominator. So when I say the top, I mean these first two fractions here. And if we multiply these second two fractions by 1 gram of copper, then that will cancel with that, and this gram cancels with that gram of copper. So now we just have chlorine to chlorine. So we have 1.116 grams of chlorine for every 0.558 grams of chlorine. So that's a 2-to-1 ratio. All right, and we can see that here in this compound here. So we have a 2-to-1 ratio compared to the copper chlorine compound in A, where copper is presented by the brown spheres and the chlorine is the green. So the copper chlorine compound in this B section, it has twice as many chlorine atoms per copper atom. It's a little bit difficult to see here, but that's what this ratio means for compound A and compound B. We found the ratio is 2-to-1. All right, and here's the practice for the first section here.